Hello, Chemistry 20. This is our first lesson in chemical nomenclature. This is writing and naming chemical nomenclature. In this lesson, we will first look at writing and naming ionic chemical formulas. This will include transition metals and polyatomic ions. Then we'll move forward with writing and naming molecular formulas, and finally we will finish with two sets of examples. Chemical formulas. They provide two important pieces of information. First, the elements, the atomic symbols that make up the compound. And then second, the number of atoms, which is identified by the subscript of each element in the compound. As we can see in blue, we have the atomic symbols of each element that is in the chemical formula. And in red, we have our subscript, our small numbers, which identify the number of each atoms in the chemical formula. Writing ionic chemical formula. The zero-sum rule is used for ionic chemical formulas. The sum of the positive valence charges and negative valence charges must equal 0. How to determine ionic chemical formula? Number 1, determine the valence charges of both atoms. Number 2, cross and drop the charges. And number 3, simplify the ratio of the subscripts between the two atoms. In our examples above, we can see the valence charges of each atom. We first have to determine these valence charges, then we can swap and drop the charges. If we look at our middle example, we can see that the +2 has been swapped and dropped. It is now a 2 subscript for fluorine. And the 1- was swapped and dropped and is now representing magnesium, but we don't have to show a 1. If we look at our first example, we have swapped and dropped both the 2+ and the 2-. But we can simplify a 2 to 2 to a 1 to 1. Therefore, our chemical formula is CaO. And in our last example, we can see that we have swapped and dropped both of the valence charges, and we are left with Be3, P2. Consider the following. Non-metal valence charges are not listed on the periodic table. That means you must remember them. Don't forget that each group has the same valence charges for every atom going downwards. Naming ionic compounds. Ionic compounds are considered binary compounds because they have two elements. That would be a metal element plus a non-metal element. The naming rules are, number 1, the metal element name does not change. Number 2, the non-metal ending changes to IDE. If we look at our two examples, we have NaCl. That would be sodium and then chloride. We are changing the non-metal ending to IDE. In our second example, we have MgF2, which would be magnesium fluoride. Notice how we are not using prefixes in ionic naming. There are no prefixes because these elements only form in one specific ratio. So there is no need to identify the amount of each atom. Transition metals. Many common metals are transition elements that have more than one possible valence, meaning they can have a different number of valence electrons. The stock system uses Roman numerals to identify the valence charge of the transition metal in the compound. For example, we can see lead 2 chloride. That represents that lead has a charge of 2+. In our next example, we can see copper 1 oxide. This represents that copper has a charge of 1+. Now, in our last example, we are looking at a chemical formula, Mg3N2. We have already swapped and dropped the charges, but if we do the exact opposite and bring the 2 that was previously the subscript of nitrogen and bring it upwards, we can now identify the valence charge of mercury, which is Mg2+. Polyatomic ions. Polyatomic ions are only found in ionic compounds. They are multiple atoms with a charge. Poly, multiple, atomic, atoms with a charge, which is an ion. Examples include NO3-, which is nitrate, HSO3-, hydrogen sulfite, and SO4 2-, sulfate. There is a list of polyatomic ions in your Chemistry 20 data booklet. Think of polyatomic ions as just another element. When naming polyatomic ions, the ending does not change to IDE. For example, if we look at NaNO3, our name is sodium nitrate. The ending does not change. And if we look at Mg3 brackets PO4 bracket 2, we have magnesium phosphate. Again, the ending does not change. Moving forward, we are going to name molecular substances. When naming molecular substances, start with the least electronegative atom, followed by the more electronegative atom. And remember, if it's a molecular substance, it's a non-metal element plus another non-metal element. The naming rules are, number 1, prefixes are added to each non-metal to indicate the number of atoms in the molecule. Number 2, the second non-metal ending changes to IDE. And number 3 is a small exception. Do not put mono on the first non-metal. Our examples, we can see CO2. Therefore, it would be carbon dioxide. Remember, we do not put mono on the first non-metal. And our second example, we have S2O3, which would be disulfur trioxide. Notice how we are using prefixes when we name molecular substances. Our molecular prefixes are, for 1, we have mono. For 2, we have di. For 3, we have tri. 4, tetra. 5, penta. 6 is hexa. 7 is hepta. Not septa, it is hepta. 8 is octa. 9 is nona. And 10 is deca. It's important to remember, when writing molecular formulas, we cannot use the zero-sum rule because molecular compounds can combine in multiple ratios. For example, we can have a compound with hydrogen and oxygen, which is H2O, but we can also have another compound, which is H2O2. This is the reason why we use prefixes, to identify the number of atoms in the chemical formula. That brings us to diatomic elements, and we have to remember these. We have first H2 So when hydrogen is by itself, it is always H2. Nitrogen by itself is always N2. Oxygen by itself is always O2. And fluorine by itself is always F2. This is the same for chlorine, which is Cl2, bromine, Br2, and iodine, which is I2. And our last two are exceptions. We have phosphorus, which by itself is P4, and sulfur by itself is always S8. That brings us to our need to know molecules. Unfortunately, we just have to know what these molecules are. We have H2O liquid. Well, that's easy. We know that's water. NH3 gas is ammonia. We also have a lot of different organic compounds, which are represented in red. Organic compounds are molecules containing carbon as the backbone. Notice how they all have carbon at the front. We also have glucose, sucrose, hydrogen peroxide, and ozone. We have to memorize these molecules. We will use these throughout the course. But there is some information that will allow us to memorize some of the organic molecules, the molecules containing carbon. If we look at each of the chemical formula, the number of carbons represents the proper chemical name. There are different prefixes for organic nomenclature. When we have one carbon, our name is methane. When we have two carbons, we are now ethane. Eth is the prefix. 3 carbons, propane. 4 carbons, butane. And 8 carbons is octane. Now, if there is an OH at the end of the molecule, it is known as an alcohol. And we just have to replace the ANE ending with OL. A good example is also ethanol, which is C2H5OH. The OH at the ending represents an alcohol, so we have an OL ending. Something else to consider. The following equation can be used to determine the number of hydrogens attached to a carbon chain. This carbon chain will only contain single bonds. And our equation is CnH2n plus 2. Which means if we had 8 carbons, we could then take hydrogen 2 times 8 plus 2. This would give us the chemical formula for octane, which is C8H18. Again, we take the number of carbons, times it by 2, and then plus 2. That will give us the number of hydrogens that will be in this carbon molecule. Example number 1. Name the following chemical formula. Pause the video and attempt this example. It's extremely important to identify whether we're working with an ionic compound or a molecular substance. They have completely different naming and chemical formulas. I can see that S4Br9, this is a molecular substance because I have 2 nonmetals. Therefore, I require prefixes. Tetrasulfur, nona, bromide. And remember, the ending is IDE. Our next example, Na3N. This is an ionic compound because we have a metal plus a nonmetal. Therefore, we do not require prefixes. We are sodium nitride. Again, the ending is IDE. Our next example, GE brackets ClO3 bracket 4. This is ionic because I have a metal and I have also a polyatomic ion. Polyatomic ions only appear in ionic compounds. Therefore, I can just write germanium chlorate. Again, I don't change the ending for the polyatomic ion. And finally, we have FeCl3. This is also ionic, a metal plus a nonmetal. But don't forget that iron has multiple charges. And when you have a metal with multiple charges, you have to show a Roman numeral. Therefore, we have iron 3 chloride. Example number 2. Write the following names in chemical formula. Pause the video and attempt this example. First, we have potassium borate. Now it's important to identify that this is an ionic compound, K3BO3. To do this, we need to find the valence charges of each element in the chemical formula. Potassium had a charge of +1 and borate had a charge of -3. So we crossed and dropped the charges and we're left with K3BO3. Our next example, sulfur trioxide. This is molecular, and since it's molecular, it tells us the prefixes. So we can just write down the prefixes as subscripts. And we have SO3, trioxide O3. Our next example, we have manganese Roman numeral 4 oxide. This is going to be an ionic compound, so therefore we have to identify the charges of each element in the chemical formula. We have Mn, which is known to have a charge of +4 because of the Roman numeral, and oxide has a charge of 2-. So when we swap and drop, we would originally have Mn2O4, but we can simplify that to MnO2. In our last example, we have barium phosphide. Again, this is ionic, so we have to identify the charge of each element. Barium has a charge of 2+ and phosphorus has a charge of 3-. So when we swap and drop the charges, we are left with Ba3P2. Moving forward, we will continue with more chemical nomenclature.